In this lesson, we're going to take the two formulas that we learned from the last lesson, and show you how to put those two together. So let me explain what a calorimeter is to you first. In a calorimeter, you usually have some kind of a container, and then inside of that container is a second container. And in between here, this is just filled with water. The inner chamber is filled with a really oxygen-rich thing, if we're doing a combustion anyway. And then usually there's some kind of a sample or something that we want to test. We want to see how much energy is in this object. So we light it on fire and it starts to burn. We know fire is exothermic. So as this is burning, it's releasing energy into its surroundings. But since it's completely surrounded by this other container that's filled with water, all of that lost energy, or that exothermic given away energy, goes into the water, and the water begins to increase in temperature. So essentially what we have is, on the inside container we have a chemical change taking place, and in the water we have a temperature change taking place. And if this was a perfect world, the amount of energy that the thing burning and losing should be exactly equal to the increase in energy in the water. So we can do some calculations to figure out how much energy was lost by figuring out how much energy was gained by the water. Okay? Now there are a few assumptions that we need to make. The first one is that the system is isolated, meaning there's no outside energy coming in, right? That would break this system. We're going to assume that the amount of energy being absorbed from the outside is very low, and that there won't be any energy that's from the inside leaking out into the surroundings either. 2, the amount of thermal energy absorbed by the calorimeter itself is small enough to be ignored. So the container themselves, this container and this container, they're both going to warm up too, but ideally the amount of water we're dealing with is a much higher mass, as well as it's going to hold a lot more heat because of that high heat capacity that we talked about in the last lesson. So there will be some energy absorbed by the calorimeter, but in order to make our lives easier, we're going to assume that whatever the container absorbs, we're just going to ignore. Third assumption, if something dissolves in water, and I mentioned this last time, if something dissolves in water, that resulting aqueous solution, unless they give me more information, we're going to assume still has the same properties as water, the same heat capacity and everything else like that. And the fourth is that the process takes place under constant pressure, because that will affect how things work, but you don't need to understand exactly why. Now, based on those assumptions, we can say that the heat that's being lost should be equal to the heat that's being gained by the water. And the heat that's being lost is a chemical change, so that's a delta H. The heat that's being gained is a temperature change, so that's a Q, from our formulas that we learned yesterday. And we can continue to expand, because I know that Q is equal to mc delta T. I know that delta H is equal to N delta HM, or we could go a little bit farther and say mass over molar mass delta HM is equal to mc delta T, or some other combination. There is a big C delta T that we'll cover in the next lesson briefly, but once we know this, we know that all of these things should be equal. So in your notes where it says D, you can expand or leave each part of the equation depending on 1, what you want or what you need to solve for, and 2, what you have. So for example, let's say that you have a question that tells you the amount of energy that you're losing. Well, the amount of energy being lost would be delta H. I don't need the whole formula, that just gives me that. And if they want to know the mass of the water, well, the only formula on the other side that has mass is right here, so I would use this. So we can come up with some formulas that mix these things together, like delta H is equal to mc delta T. Now the trick with these formulas is to keep these separate. This is the delta H for the, in this case, the fuel, and everything on the other side, this mc delta T is for the water. So make sure that we're keeping those straight in your head. But you could do, and maybe I'll use colors to show this. You could use, mass over, that's a little ugly, over molar mass, delta Hm is equal to Q. Or we could use N delta Hm is equal to mc delta T, the full one that we used yesterday. Any combination of those formulas will work because they, in theory, if we use those assumptions, they should all be equal. Okay, now in your notes in E, it talks about the state of water. This is just something to show you because we're going to come back to it later on, but I want you to at least have this in your mind. If you're looking at a chemical reaction, we know that combustion typically has the products of CO2 and H2O. If it's a combustion system, those are both usually gases in any kind of an open system, right? You're not producing a puddle of water underneath the fire. It's just vapor that goes up into the air. But in a calorimeter, you're going to get CO2 gas and H2O liquid. That's not going to play a huge part right now in any of our calculations, but I just want that to be in your mind because it is going to change things pretty significantly later on. And also keep in mind that in a living system, like if we were talking about photosynthesis or cellular respiration, even though those formulas look very similar to a combustion reaction, they are also going to have water liquid, not water gas, because it's inside of a living thing. And it has to do with enzymes and all sorts of other things, but that'll be water liquid, not water gas. So that's kind of the intro to what you need to know. In the next video, we'll look at a couple of examples and just make sure that this clicks on how to use these together.